Oh, hi there. Welcome to Stefan's Garage. Today we're going to talk about the charging system on this 1981 CB750. More in particular, we're going to create a DIY Gaussmeter to be able to assess if your alternator rotor is functioning properly. The charging system on this motorcycle consists of four main components. You've got the rotor or field coil, you have the stator, you have the regulator and rectifier, which is actually two parts, but they're in the same package, so we'll call them one. And then you have the battery. Once you have all the associated bodywork and the seat off, you'll want to disconnect the battery before you go any further. Then we'll take off this right side engine cover and reveal both the stator and the rotor. Pulling the stator cover off. Inside you'll see the stator here and the rotor here. Old rotor sitting here on the bench. This one failed some time ago, so I was able to do a little dissection on it. I'm going to pop the top off here, which is not usually done. I had to actually break this one in half to be able to remove it from the crankshaft. You can immediately see the claws, and we'll focus on the bottom portion where you can still see the field coil inside. The field coil is approximately 20 millimeters by 16.5 millimeters with 22 gauge wire, and I got about 860 turns out of the calculation on that. So when the field coil is complete, of course, and is excited by the slip rings, it has a current going through it. It creates a magnetic field. You can calculate the magnetic flux density of this field according to Gaussmeter's law. And essentially, depending on which way the current's going and that magnetic field, that magnetic flux density, is traveling through this iron or steel core, and according to the right-hand rule and the current's direction, will make one of these poles positive or one of these poles negatives, I believe. Now, a typical failure mode of this particular rotor design, and I believe what happened to this one, is that the inner windings have is magnet wire, and they have a let's say a protective and insulating coating around them. That coating starts to break down, and it breaks down in a place that you can't really see or get to. Well, what happens is the field coil shorts to itself. Therefore, when you're supposed to get 860 turns in your coil and the corresponding magnetic field from that, you now only have maybe 200 turns, or wherever the short may be. Now, according to Gaussmeter's law, if you have less turns in your coil or less amp turns, then you're going to have a decreased magnetic field. And it can decrease to the point where you're not exciting the stator coils enough to charge the bike properly. So what I've proposed is to measure the magnetic flux density somewhere near the coil. Well, how am I going to measure the magnetic flux density this far away from the field coil? The best way to do that is from a Gaussmeter. And hold on tight, because I'm going to throw a lot of guys' names at you here, and you should definitely look them up because they're pretty influential to this field, no pun intended. So, Gaussmeter. Gaussmeter works off the Hall effect. The Hall effect is based off Lorenz's law. So, this Gaussmeter is all based around the Hall effect sensor. So let's talk a little bit about the Hall effect sensor. Edwin Hall discovered in 1879 was really based off the Lorentz force. So if I have an input voltage or a current going across what's in here, which is a semiconductor material, and I got electrons flowing across it, I've got the QV term of Lorenz's law here, and then I cross that with a magnetic field that will be impinged on the front of this sensor here. So I could say with the right hand rule, I go forward QV and then down, and I have a Lorentz force in the bottom direction, or if the current's flowing in the opposite direction, then I have it in the upward direction. The key here is that the charges on this semiconductor are repelled to each side of the semiconductor material. And when you connect each side of the semiconductor material, you're able to get what is known as the Hall effect. Now, in order to turn a Hall effect sensor into a Gaussmeter, all you have to do is create a simple circuit and create the Gaussmeter, or what I like to call a Gaussmeter. I'm going to get my lead here and turn my my cheap multimeter on here, and you can see my steady state voltage is about 200 millivolts. Now, the best way to use a Gaussmeter for this application is to get a discrete measurement, which would be to use a linear Hall effect sensor. Now, that would be great if I would have ordered the right Hall effect sensor. Now, if I would have ordered the correct linear Hall effect sensor instead of a switch, all I would have to do is tape the Hall effect sensor to the center portion of this outside of the field coil, essentially. Now, I've done the measurements here. The measurements are, don't bump the camera, just kidding, that's not the measurements. The measurements are really, it's about 50 millimeters from the edge of the coil to the top of this cover. Just kind of set this up so you can see the Gaussmeter and the Hall effect sensor all together here. And I'm going to turn the bike to accessory on a 3 count. That is 3, 2, 1, and go. Stand by. Technical difficulties. I flipped it over to park, which is past accessory. Now it's on accessory. And you can see the Hall effect sensor switch over. So you can see me turn it off. The Hall effect sensor will turn off. Boom. Be very repeatable here. Turn it to accessory again. And so this has been a DIY Gaussmeter on Stefan's garage on checking out the rotor on a CB750 Honda. Thanks for joining me on this project today. I'm going to go ahead and get this CB750 back together. It's going to turn into a beautiful evening. I'm ready for a ride. So I'll catch you next time on Stefan's garage.